In lesson 4.6, we are going to be talking more about proving our triangles congruent. We're going to add to the list of shortcuts that we can use to prove triangles congruent. And one of the things we're going to start out by talking about is the included side. The included side is the common side of two consecutive angles in a polygon. So in my diagram, if I were looking at angle P and angle Q, the side PQ would be my included side between angles P and angle Q. Remember that I've said before the word included kind of means in between. It is in between angle P and angle Q. Now, another shortcut that we are going to add to our list for proving triangles congruent is the angle side angle shortcut. Angle side angle they're going to abbreviate as ASA, where the side is included between the two angles. So the reading of that is going to say if two angles and the included side of one triangle are congruent to two angles and the included side of another, then the two triangles are congruent. So as you look at the diagram of the two triangles here, they are showing you the angle side angle. I have angle G congruent to angle K, side GH congruent to side KN, angle H to angle N. Angle side angle, angle side angle. Looking at example A, when they ask me about the triangles which triangle would be congruent to triangle CAT by the ASA shortcut or ASA postulate, I find my triangle CAT, angle side angle. I'm wondering which one would be congruent to that one. Well, as I look at my two options, I'm wondering if it's triangle 1 or triangle 2. Looking for ASA, I'm going to have to say it's going to be triangle DOG. Triangle DOG is the one that shows me angle side angle with the side included. The other one actually has angle side or side angle. Okay. Question 2 says, can you conclude that INF is congruent to either of the other two triangles? At this point, we're going to have to say no, it cannot be determined. Based on the information marked, it does not show one of the shortcuts that we have talked about. As I look down below, they're wanting me to prove triangle NML congruent to triangle NPO. We know that we start our proof with our given information, so we're going to go ahead and take number 1 and say that NM is congruent to NP, and that angle M is congruent to angle P. I also like to make sure that that is marked on my picture. NM congruent to NP, angle M congruent to angle P. They do have the markings in the diagram, but sometimes we have to add them in ourselves. Now, as I look at my picture, I'm wondering what else is true or what else can I mark? Sometimes students want to mark LN congruent to ON, but in this case, we don't have any justification in order to do that. I don't know that it is being bisected or that N is the midpoint of that segment. So I cannot mark something simply because it looks like it is the same. However, I do see in that diagram that we have a set of vertical angles, and I can go ahead and mark that. If I come over here in my proof, though, when I make a marking, I need to make a statement. I actually need to name those angles with 3 letters. I cannot just simply say angle N. So I'm going to say angle LNM is congruent to angle ONP. How do I know they're congruent, or why is that the case? Well, because they are vertical angles. And so we can say definition of vertical angles or just simply the vertical angles theorem. Either would be fine. But just by making that marking, I now have proven my triangles are congruent because I have shown the shortcut of angle, side, angle. Both of my triangles show congruent angles in the included congruent side. So I, in step number 3, can say triangle NML is congruent to triangle NPO. Reason being, using the shortcut ASA, or angle, side, angle. I will also point out to you that it's important to include your symbols in your statements because angle LNM is a different statement than saying triangle NML. Okay. Taking a look at the top of page 2, again they're asking me to prove congruent triangles. And we know that we would start out the same. We would take our given information, and that would be our first step. And in our given information, they're telling me that angle A is congruent to angle X, angle B is congruent to angle Y, and side BC is congruent to side YZ. As I look at my diagram, I'm trying to decide, is there anything else that I can mark? And as far as the side lengths go, there's nothing else that I could mark congruent because I don't have any justification to mark the sides congruent. But I will tell you that I could, in my picture, mark angle C congruent to angle Z. What kind of reason would I give? Well, that would be by the third angle theorem. And now, I actually, with that marking, have shown the angle, side, angle shortcut. So I can say that triangle ABC is congruent to triangle XYZ. Angle, side, angle. Well, would you agree that my given information to start out with, they had given me 2 angles and then the side. 2 angles and a side. So angle, angle, side. If I know 2 of my angles, I am always going to be able to prove that third angle congruent with the third angle theorem. So thus, this really tells me if I'm given angle, angle, side, it will always work because it will always also turn into angle, side, angle. Which means angle, angle, side ends up being another shortcut to proving my triangles congruent. Angle, angle, side is going to be AAS, where we have 2 angles and the non-included side. If I have 2 angles and the non-included side shown congruent to 2 angles and the non-included side of another triangle, that is enough to prove that my triangles are congruent. Taking a look down below, in my diagram here, they're asking me to prove triangle ABC congruent to triangle CDA. We know, as before, we're going to start out with our given information. Angle B is congruent to angle D. And here they're telling me that side AB is parallel to side CD. Now, just because my 2 sides are parallel does not necessarily mean they're congruent. So I cannot mark them congruent. However, I can say that if I have some parallel lines, it usually tells me something about my angles. And in this case, I'm going to look for an angle pair. Well, do you see that if I kind of extend them, I think it helps me to see my angle pairs. If I looked at side AC as being my transversal, then I actually have a pair of alternate interior angles. Sometimes kids are confused with which ones would be the alternate interior. Well, the alternate interior angles actually happen right here and right here. Your alternate interior angle needs to touch your parallel line and your transversal. So when I go ahead and mark those congruent, I need to make a statement about it in my proof. I'm going to say that angle BAC is congruent to angle DCA. How do we know they're congruent? Well, because of my parallel lines, the alternate interior angles theorem says that they are going to be congruent. Now, I don't quite have enough to say my triangles are congruent. I really only have two angles. However, in that diagram, do you see that those two triangles do have a shared side? So I can go ahead and mark my shared side congruent, but if I make that marking, I need to also come over here and make a statement about it in my proof. My statement will look as so. Segment AC is congruent to segment AC. Something being congruent to itself, well, in Chapter 2, we said that that was the reflexive property of congruence. And now I can actually say, well, this shows angle, angle, side, shortcut. Now I will tell you that angle, angle, side in some textbooks is written as side, angle, angle. It means the same thing. So my triangle ABC must be congruent to triangle CDA by using the angle, angle, side shortcut. I'm going to go ahead and make my markings a little bit darker on this diagram so that you can see them a little bit easier. Previously, we had said that the side-side angle shortcut will not work to prove triangles congruent. So we cannot use side-side angle. However, there is in one specific case a time when that will work. And that case happens when we happen to have a right angle. If I have two sides and a right angle, that will show me congruent triangles. Since this is a right triangle, they actually call this the hypotenuse leg theorem, HL. The HL theorem says that if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and leg of another right triangle, then the triangles must be congruent. So in order to use the hypotenuse leg theorem, we need to make sure that we have, number one, a right triangle. Secondly, we need to know that the hypotenuse of each triangle are congruent and that one of the legs is congruent. In example C, they're asking us to decide if we can use the HL congruence theorem to prove our triangles congruent. So as I look at diagram number 1, I see, well, if this is a right angle, this has to be a right angle because they're a linear pair. And they do have their hypotenuses marked congruent. I would need to know that one of my legs is congruent. And in fact, I know that this is a shared side, and so hypotenuse leg, yes, I can say that that will work here. In the second picture, I see that they both have the right angles and they both have a leg congruent. I'm wondering about the hypotenuse. Well, this hypotenuse and this hypotenuse, they do look the same, but at this point, I can't really justify why I would mark them congruent. So I'm going to have to say no, at this point, I cannot use the HL theorem. I really do not have enough information to determine. As I take a look at writing a proof down below, I can see that we're trying to prove our triangles congruent. In this case, they do tell me that I have some perpendicular bisectors. They also tell me that side CD is congruent to side EA. Where can I go from here? Well, going back to the initial part, AD is the perpendicular bisector of CE. That really means that my segment CE is the one being bisected. So I can go ahead and mark those tick marks, but if I make that marking, I have to go ahead and make a statement about it. Segment CB must be congruent to segment EB by definition of my perpendicular bisector. And in this case, I do see that I have vertical angles. However, if I mark vertical angles, I would simply have the SSA shortcut, and that doesn't prove triangles congruent. So I'm going to go back to my givens. It actually says that AD is the perpendicular bisector of CE. Perpendicular meaning that, well, this angle must be a right angle and this angle must be a right angle. So in my proof, I'm going to go ahead and say angle CBD must equal 90 degrees and angle EBA must equal 90 degrees. And I'm in fact going to go ahead and use the same reason. It is because of my perpendicular bisector. Now, I actually see, oh, these are right triangles, and I have shown the hypotenuse leg theorem. Now, if I was being really thorough, I probably should go ahead in my proof and say that triangle CBD is a right triangle, and triangle EBA is a right triangle. Why do we know that? Well, by definition of a right triangle, it has to have one right angle, which would then allow me to say, well, those triangles must be congruent. Because we can use the hypotenuse leg shortcut. Finally, in example D, we want to take a look at proving our triangles congruent. Identify the postulate or theorem that would prove them, or identify the shortcut. So in summary, I want to let you know that when we talked about our shortcuts for proving triangles congruent, we talked about using SSS, SAS. Today, we talked about ASA, AAS, or hypotenuse leg. Ones that will not work as shortcuts were the angle, 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 or the side, side angle. They do not prove our triangles congruent. So that's just a good summary to kind of keep in mind here. As I look at my diagrams for 1, 2, and 3, sometimes there's different proofs or different shortcuts or reasons you could use to prove your triangles congruent. In question number 1, I have a 150 angle and a 15-degree angle, and I also have this shared side. Well, I would have to say yes, we could prove these triangles congruent. They actually are showing me angle, side, angle. Both of them match up. Angle, included side, and another angle. In question number 2, we have these 90 degrees, which means we are going to have some right angles. I have both of these side legs, well, actually the hypotenuse, and so based on that, I'm going to say yes, we could use the HL theorem. But also looking here, I see there's a shared side, so I could also say, well, side, side, side. And actually, because this large triangle is isosceles, we could even say SAS or ASA. In fact, any of them would work for number 2. In question number 3, they have these angles out here marked congruent, which means by vertical angles, I could mark as so. We could say yes, we could use SAS. But again, I have a shared side. I could also say SSS. If you have more questions about using the shortcuts to prove triangles congruent or how you identify which shortcut to use, please come in and see me. You can also check out more example videos that are provided by our textbook